So this is session number 3 in respiratory. This is the oxygen hemoglobin dissociation curve. The general statement, again, says that we have a heap of combined talks here. Knowledge builds between talks, and particularly in these couple now. We'll run through a question and how the questions are asked. We'll do the background information that's required to answer the question. Hopefully you can answer a model answer for you to have a look at. Oxygen hemoglobin dissociation curves are a big part of the respiratory exam. You'll see it asked very often, and there's only a few different things that they ask. So know this one well, and you'll get through quite easily. The way in which these questions are asked relates to drawing of the oxygen hemoglobin dissociation curve and knowing the factors that shift it. The particular examples we have here says that how is oxygen carried in the blood? Again, part of the big picture which we'll run through, and that relates to carbon dioxide eventually as well. Draw and label the oxygen hemoglobin dissociation curve. What are the implications of this curve's shape? What factors cause shift in the curve? What are the effects of carbon monoxide on hemoglobin oxygen transport? All of these different ways of asking a very similar question, and it all relates to oxygen transport within the tissues. So what we're talking about with the oxygen hemoglobin dissociation curve, eventually we'll get to this diagram, which relates PO2, saturation of hemoglobin. And it's a curve that has a particular shape, with a flat portion, and a steep portion, and some particular numbers that we'll go through. And that for a given set of numbers, this curve can move, i.e. creates different conditions of the amount of oxygen sitting in the blood to the amount of partial pressure or tissue pressure of oxygen. And that's advantageous, and we'll talk through that. To get to that stage though, we've got to understand where oxygen sits in the blood and why blood is advantageous for oxygen transport. To do that, we're going to start from scratch and build some blood. Essentially what we're talking about here is a pool of liquid, i.e. our blood, or more particularly the plasma portion of our blood, that is in exchange with a source of oxygen, the air. And there exists some sort of a membrane. We start to build our blood by saying this is just the liquid-air interface. And we have oxygen in the atmosphere, and through Henry's law, it will diffuse into the liquid. And it will diffuse into the liquid at a rate that is proportional to the partial pressure in the air, i.e. 21% of 760 millimetres of mercury if we talk about usual air. And it will diffuse and equilibrate to have the same partial pressure in the liquid as it does in the air. Now, that is a predictable proportion, in that if we talk about plasma now, and we talk about alveolus, we know the amount of oxygen, or the oxygen content, and that's very important. I want to put emphasis on the content here. This is the amount. If you could pull it out and weigh it, how much would there be? The oxygen content is a proportion of the partial pressure. And it just so happens that for oxygen it's 3%, 0.03 times its partial pressure. So what we end up here is the oxygen content in this plasma is its partial pressure times 3%. So if we have roughly 140 millimetres of mercury partial pressure of oxygen sitting in our alveolus, diluted with water comes down to approximately 100. And we take 3% of that, what we have is 3 mils. 3 mils of oxygen will be dissolved into the blood, or into the plasma portion of the blood. Now, the overall content there is not much, considering it takes a human approximately 20, 25, and sometimes up to 100, depending on the exercise circumstance, mils of oxygen per minute to survive. Then what we're talking about here is not much oxygen at all. So if we rely on Henry's law and diffusion from gas into liquid, we're only going to load a very small amount of oxygen. That's not enough for life. So what we want to do is modify our blood a bit. The concentration gradient that governs movement of oxygen across this surface is determined by the concentration there, just on that side, and the concentration in the plasma, just here, just on the other side. What then occurs is the oxygen moves, diffuses throughout the liquid, such that the oxygen that was sitting just under the surface here moves away and creates room for more oxygen to move in. And that all occurs right at the surface of the liquid. What we're going to do when we build our blood is try to design a system that removes oxygen from that liquid, therefore maintaining this concentration gradient and allowing more oxygen to load into the liquid. And in fact, we do that by adding a red blood cell. So what we're now going to do is have a pot of blood. Again, has a surface between air and liquid, and allow it to equilibrate such that we have 3% of the partial pressure of oxygen dissolved into the liquid in this relationship. What we're now going to do is put a compartment in here. And this compartment is going to exchange oxygen with the liquid as well. This compartment will remove oxygen from the liquid and store it in the compartment. And in fact, we'll put some properties in this compartment that remove the oxygen from participation in the concentration gradient between here and here. So we're going to package this oxygen up now and take it away from the exchange medium such that more oxygen can move. And we'll pack that in there too. And allow more oxygen to move. And we'll pack that in there too. In fact, we'll do that 4 times. More oxygen goes into that compartment. And what we've done is, within our compartment, created a place where that oxygen no longer participates with the concentration gradient between those two compartments. What that then does, in turn, allows oxygen that was in solution here to move into this compartment and be packaged away. Meaning the oxygen that was in here is no longer, meaning more oxygen can diffuse in from outside. And when that oxygen comes in, I'm going to put another compartment in. And put in this molecule that will pull in 4 lots of oxygen. Removing it, again, from the liquid, allowing more to diffuse in from outside. So what I've done here in creating these compartments is I've locked away the oxygen, not allowing it to participate in equilibration. Obviously, these compartments will fill up, so I can add more of them, and add more, and add more. Of course, what I'm describing here is blood with a red cell and a haemoglobin molecule that takes oxygen from alveolar gas across the respiratory membrane and locks it away 4 at a time onto haemoglobin, allowing a concentration gradient of oxygen to be maintained and therefore changing the overall content, the overall measurable mass of oxygen that's available in this blood. So what we've done by doing this is making this blood heavier with oxygen. Rather than just 3%, we've added a whole lot more oxygen into this compartment here, into the red cells. That still only sits at 3% dissolved in here, but there's a flux, there's a transition through the liquid phase into the compartments. So if we've designed blood, what we're now talking about here is plasma. We're talking about the red blood cell. We're talking about the alveolar membrane. And so by adding this compartment, we've increased the mass of oxygen that can be carried by blood. And there's a few properties here that we know that are experimentally measurable, and we can determine how much oxygen is available in the blood. So we talk about dissolved oxygen. When referring to oxygen content of blood. And we also talk about bound oxygen onto haemoglobin. Note, it's the dissolved oxygen content, this 3%, which participates in tissue oxygen exchange. It's not the red blood cells. They merely act as a reservoir. But the reservoir of how much content is in the blood is largely governed by the haemoglobin. We know that 1 gram of haemoglobin can hold 1.3 mils of oxygen. And so if we know how much haemoglobin we have, gram percent, or whatever measure you want to use, we'll change this factor. But each haemoglobin holds 1.3 mils of oxygen. And we know how saturated that haemoglobin is, i.e. how many of these 4 binding sites are occupied. We can then work out the content of bound oxygen in the blood. This comes out at about 3 mils. This comes out at roughly 18 mils. If we make some estimates on haemoglobin at being roughly 150 and saturations being roughly 95 to 97%, meaning that we come out with 21 mils of oxygen held in every 100 mils of blood. Now that is enough to sustain life. The oxygen content, the amount of oxygen deliverable to the tissues, is large. And it's far larger than relying on just dissolved oxygen alone. Of course, there are ways to try and boost how much oxygen is dissolved, and we can increase the PO2. And if we increase it far enough, we'll arrive at a value like this. But this has to go into the hundreds and thousands of PO2, i.e. very high pressures, for dissolved oxygen to be able to facilitate this. That's why we need haemoglobin in the blood. That's why anemia is such a problem. So, using that concept of building a blood, knowing where in the blood the oxygen is bound, where it's available from, we allow cardiac output to provide flow to the tissues. And when we provide flow to the tissues, every 100 mils of blood that flows into the tissues provides 21 mils of oxygen. What we're now going to talk about is the properties of oxygen content when it's exposed to different environments. i.e., if there's an environment with a low PO2, then 3% will be dissolved oxygen, and that will change a little. But compared to the 21, a change of a few percent of 3 mils is not much. Whereas when we get out to here, we talk about the bound oxygen. This is where a lot of our oxygen is held. And so if we talk about changes in the environment in which this haemoglobin sits, that affect the amount of haemoglobin, the amount of oxygen held on the haemoglobin, then we're talking about a dramatic change in the amount of oxygen that's held in the blood. I.e., the oxygen content of the blood is largely proportional to the haemoglobin and its saturation. Now I want to introduce the term haemoglobin saturation. This is the thing that appears on the oxygen haemoglobin dissociation curve. This is not the thing that determines hypoxemia of tissues, of blood. This is not the thing that determines precisely how much oxygen is in the blood. It is very closely related, and it does so by this formula. But when we talk about saturations, we talk about a thing that is very easy for us to measure clinically for our patients by sticking a peg on their finger and putting some red light through it. For convenience, that's what we use. The inference here, though, is oxygen content. I want to make that very, very clear. If you can get that concept, you can now understand this diagram. The questions that are asked on this diagram relate to oxygen content, but it's displayed in terms of the thing that's easily measured, oxygen saturation. And the other thing that's easily measured, a probe stuck in a tissue to measure the PO2, i.e. the gaseous phase of a solution with air above it, i.e. a blood sample. We're going to get a test tube and take a sample of blood, and the way that this is measured is to allow equilibration of oxygen in the test tube above and below, and then you sample and measure this. And that's what your PO2 is. So that can be a blood sample, that can be the tissue that we're perfusing. But that's where that value of PO2 comes from after equilibration. That value is not related to oxygen content directly. You'll see if we measure the oxygen content of this piece of blood, it's largely related to this, less related to this, and therefore the PO2 doesn't give us a good description. This diagram relates that description. All right, so we make the differentiation of oxygen content, know that we can conveniently measure saturation, and it's related to anemia and pathologies through the number of hemoglobin molecules we have or the number of red cells. What we now want to do is talk about constructing this curve. This particular curve, we'll leave that one up. This particular curve has several important features. Again, when we draw a curve anywhere in these vivas, we talk about axes, we talk about labels, and there's a few important labels. 30, 60, 60, 90 are the numbers to remember. Really simple. 30, 60 corresponds to a point, 60, 90 corresponds to a point. And we can draw our curve through that. That defines a few important areas. Sitting up here will be 100% as well. You'll note that the curve attains it and then starts to get away from it. There's a few things to note on this curve. The features of the steep portion and the features of the flat portion. The steep portion of the curve describes a situation where for a given change in PO2, and we'll talk about what that means, just move that a little. For a given change in PO2, we create a change in haemoglobin saturation. What does that mean? For a given change in PO2, we create a change in the saturation of haemoglobin. We know we're talking about oxygen content. So a change in PO2 here doesn't do a lot to our overall content. But a change in the saturation does a lot for our content. So the inference here is that there's a large change in content of blood. If we talk about a small change in PO2 on this steep portion of the curve. I'll say that again. For a small change in PO2, i.e. this portion here on the steep part of the curve, we create a large change in relative terms of change to saturation. That change to saturation is the thing that determines oxygen content, and that's why it's of interest to us. The small change in PO2 that occurs is a drop that occurs when we go to the venous side of the circulation, or the tissues. So for a change consistent with venous PO2, we end up with a relatively large drop of saturation, a relatively large drop of oxygen content. And that's desirable in the venous tissues. Now we take it back to the situation in the flat part of the curve, where in the lung we see a difference from the steep part of the curve to the flat part of the curve, i.e. a larger increase in PO2. In a large PO2 environment, or an environment where the PO2 is relatively large, we end up with a very large increase in the saturations. An increase in the saturations is an increase in the content. So in an environment where there's lots of oxygen available, the haemoglobin becomes very saturated and our oxygen content is increased. What that says is that the steep portion of the curve relative to the flat portion of the curve is associated with large change of oxygen content as opposed to small change of oxygen content. And that's desirable between the lung and the tissues. Now, that is the point that is often asked about these haemoglobin dissociation curves. Explain the steep portions and explain the flat portions. If you can describe for a given change in partial pressure of oxygen, or in the environment where partial pressure oxygen is low, it's associated with the steep portion or a large change in saturation, compared to not much change in saturation, what you're talking about here is the inference of oxygen concentration. Other factors that are often related to this curve are how does this curve change? So for a given curve, I'll leave it there, we can shift the curve to the right. Think about what a shift to the right means. What a shift to the right means is that in a situation where we have normal venous conditions, low PO2, there was this much content of oxygen, this much saturation in the blood, i.e. that correlates to oxygen content. If we shift this curve for the same venous conditions, what we have is a lower saturation, i.e. a condition for a given PO2 where there is less oxygen saturation, less oxygen content. So the oxygen that was held in the blood is now no longer there. It's been given up to the tissues. So the right shifting curve facilitates offloading of oxygen from the blood into the tissues, because for a given PO2, the saturation is less on this curve than it is on this one, i.e. the content is less on this curve than it is on this one. Saturation and content. We're trying to use the two interchangeably and they're related like this. Now, you'll be asked about factors which move this curve. They're really simple to remember. If you think about a person doing exercise, they're associated with a few things. If they run away from the origin, their origin, or the 0 point on your curve, they will be creating heat. They will be creating hydrogen ions. They will be creating 2,3-DPG. They will be creating carbon dioxide. These are the classic factors that are known to shift the curve to the right. They are also the factors that occur when someone exercises. They produce heat, acid, CO2, and metabolite. So a simple way to remember that. If you think about what exercise does, it consumes oxygen. If you consume oxygen, the oxygen's got to come from somewhere. The only place it can come is from our constructed blood. Our constructed blood holds an amount of oxygen that is dissolved and bound, and the overall amount is largely contributed to by the bound portion. In an exercising person, hemoglobin is not going to change much. The constant stays relatively the same. PO2 is certainly not going to change much. Atmosphere hasn't changed. The thing that's going to change is our saturation. It's therefore desirable as we exercise to offload the oxygen that was bound in the blood to a lower saturation than it would have been if we weren't exercising. I hope I've stressed that point enough. That's a really important point. If you can talk about content, you'll get through the changes that occur in this diagram. Okay, we'll move on to a question. We're starting with physiology. A 40-year-old man with acute pancreatitis is hypoxic. How is oxygen carried in the blood? Oxygen is carried in the blood in two forms. It's dissolved and it's bound to hemoglobin. The dissolved portion is 3% of the PO2, and the bound portion is 1.3 mils of oxygen bound to each gram of hemoglobin in proportion to its saturation. And this is how we define also the oxygen content of the blood. The second part of the question is draw and label the oxygen dissociation curve. The oxygen hemoglobin dissociation curve describes a curve relating the PO2 of blood to its percent hemoglobin saturation. It's an inference about the oxygen content of blood. The curve has a unique shape in that there is a steep portion of the curve and a relatively flat portion of the curve. At 30%, so PO2 of 30, hemoglobin is roughly 60% saturated. At a PO2 of 60, hemoglobin is roughly 90% saturated. The steep portion of this curve describes a situation where small changes in PO2 result in large changes in saturation. This is desirable in relatively hypoxic environments, such as the venous side of the circulation and in the tissues. The flat portion of the curve describes a situation in which large changes in PO2 don't change saturation a great deal. This is desirable. It is desirable to have small changes in hemoglobin saturation in areas where there are large changes in PO2 or high PO2, such as the lung. This overall facilitates loading of oxygen onto hemoglobin and into the blood. What are the implications of this curve shape? We've already been through.